So today, even though our main focus is going to be in theoretical probability, okay, what should happen, we're still going to do some review of some of the other things that we've been talking about before. So, theoretical probability. It's a measure of how likely something is to happen. Like, we're not going to actually experiment, we're not going to roll a die, we're not actually going to pick a card, but we're going to kind of figure out, okay, if everything's equal, what should happen here? So then again, the set of all those outcomes is called the sample space. We haven't talked about it that specifically that way before, but it's more of a mathematical term that we can look at. And then for equally likely outcomes, the theoretical probability of an event, P of E, E stands for event, whatever that event happens to be, is the ratio, and again, a ratio is just a fraction, okay, of the number of favorable outcomes, which we before were calling successes, you know, what I want to have happen, to the total number of outcomes possible. Okay, and that number is going to be somewhere between 0 and 1. 0 being it never will happen, and 1 being that it'll happen every time. So, simple events, and we won't do all of these because it kind of goes back over what we've done. But again, a jar contains 32 red and 28 blue marbles. What's the probability that a randomly selected marble is red? You're like, okay, success is red, 32. What number is going to go on the bottom, though? How many marbles are there? Okay, I can't just put the 28 there. The bottom is going to be the total number of marbles, in this case, that are available, which would be 60. And we've even talked about, for these first couple of days, the importance of reducing. And again, whether you do that in your head, or whether you bust out a calculator and you're like 32 over 60, little math, enter, 8 over 15. Okay, we always want to reduce to that simplest fraction. Okay. So we kind of start looking around a bit. We're like, okay, 2 even, since we got into this a little bit before the notes today. Okay, a letter in the word restoration is randomly selected. What's the probability of selecting a vowel? And again, we're just talking about A, E, I, O, U. We're not getting into the special cases. So I start to look, and I'm like, okay, well, let's see here. Vowels. 1, 2, 3, 4, 5 of those, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 total letters. Now, if the situation was the opposite, maybe it said a consonant or not selecting a vowel, if I had any confusion with what the parts were, maybe I take the part that I do know. Maybe I know the vowels and I count them up and I just subtract from 11, and I can find it that way. Okay. Now, sometimes even with a simple event, things can get a little more complicated, especially if there's a part of it that I have an issue with. So let's say, for instance, we get up to number 3. A day in the month of January is randomly selected. What's the probability of selecting a prime number? You're like, oh crap, I don't remember what a prime number is. Prime numbers are numbers where only 1 and the number go in. And you're like, well, how in the heck am I going to know that? Sometimes, not every time, sometimes you may literally, if you have to think about it, you may need to list out some values. And sometimes on something like this, it may not be the most convenient thing to do, but I'll be honest, I know very few people that would be able to answer this question just kind of thinking about it off the top of their head. You might be able to come up with some of the values, and of course I have to pick January. I have to pick a long-numbered month. Couldn't have just picked February here. Okay, so prime numbers, 1 and itself. So for most of my smaller values, this is going to take care of most of them. Now the first one I get into an issue though is 4, because 2 goes into 4, so that's not prime. But 5 would be, 6 goes into, 2 goes in, 3 goes in, and I kind of just keep working my way along, and as I get a little further, it's going to be harder to find some where some other number doesn't divide into them. 2 goes in there, 3, 2, nope. Nope. And I can't even say it's all just like odd numbers, because you'll notice like 15 worked. That works, yep. Nope. 5, 3, 2, 3, 2, nope. Okay, let's see where we're at here. 1, 2, 7, 8. Ooh, I did one thing silly. 1 is not prime because you can't have it with 1 in itself. I almost forgot my own rule. Bad math teacher. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's better. 11 out of 31 possible days. So there are times where you're not just going to be able to do this off the top of your head. You may have to do some work. You may have to draw something out to figure that out when you're doing these. Okay. I want to go back to a card problem next. So again, I look at something like that and I go, okay, what's the probability of drawing a heart or a club from a standard deck of cards? Okay. Now again, or means as long as either one's happening, we're fine. So a heart, there's 13 of those out of 52. Okay. Or a club, again, there's 13 of those out of 52. None of them overlap because hearts and clubs are different things. And the reason, again, I keep these this way at the start is so I have a common denominator. And then, of course, I reduce my fraction. And then we're going to go past number 6 right now because we're not dealing with the permutation combination part of things here. If we need to come back in a bit to 4, we can, but I don't want to go overkill here on you. Okay. Now, this next part we have discussed, but we haven't discussed it, again, with the proper terminology here yet. It's called the complement of an event. Okay? The complement of an event is the probability that the event doesn't happen. Okay, what's the chances of me not getting a 6 on this roll or not drawing a face card? So since the sum of all your probabilities always equals 1, because the do's and the don'ts always add up to one of the other happening, then the probability of not getting E is 1 minus the probability of that happening. So for instance, the probability that it will snow tomorrow is 7 out of 20. That better not be realistic, even though I wouldn't doubt it at this point. What's the probability that it will not snow? It would. And some of you may say, Harty, I could have figured out that was 13 out of 20 without doing the 1 minus part, because if 7 parts are yes, and there's 20 total, 20 minus 7 is just 13. If you know that off the top of your head, I say go for it. You can keep going. Okay? That's fine. And then we'll do number 8 here, and then I think we'll have the point across. So a month of the year is randomly selected. What's the probability of getting a month that does not begin with the letter A? Okay, let's think about this for a minute. 1 minus the number that do might help us a little more here. So let's see. What months start with A? April and August. So 2 out of 12. Which means there's 10 left that don't start with the letter A. And again, I just want to make sure that I get that reduced. So again, just 1 minus what it is. But again, some of you may look at that and go, well, I can just tell you the 10 that are. That's fine. Okay. So again, we're still kind of doing some overview here, just kind of seeing how this works. So now we go back and hit up another thing that we talked about a couple days ago, dependent, independent events. Okay. When one outcome doesn't affect the other, they're completely separate. Before, the example we used was if I roll a die and I draw a card. Whatever I roll on the die has nothing to do with what card I'm going to draw. So when that happens, we take the probability of the two events and we multiply them together. If they're dependent, so let's say I'm drawing cards and I draw a card and I draw a king, but I keep that king out of the deck, bless you. Now, the number of cards available has decreased, so that does affect it. So I still would do the probability of the first event, but then I'm going to multiply that by the probability of my second event after A happened. So what's the probability of me getting a king if I've drawn a king already? And we look at the different parts of that. And we're going to look at an example, well, examples of each of those. Okay. So independent events. Let's take a look at a couple of things here. Okay, a die is rolled 3 times. What's the probability of getting 1s on each roll? Okay, 3 separate things. I roll a die the first time. What's my chances of getting a 1? 1 out of 6. Okay, so is that going to make any difference when I pick up the die and roll it again? No. So it just means, since I'm rolling it 3 times, I'd get 1 out of 6, 1 out of 6, 1 out of 6. So theoretically, for me to roll a die 3 times and get 1s 3 times in a row, it'd only happen about once every 216 times I'd try to do it. That could take a while. That's why we like theoretical sometimes. Okay? Or if I toss a coin and then day of the week is selected. What's the probability of getting tails? 1 out of 2. Then getting a day starting with the letter T. 2 out of 7. And I multiply it out and reduce. Again, tossing a coin, picking a day of the week. Completely unrelated. Okay? And then I just want to do one of them down here. Well, actually, yeah. No, I want to do 2 of these. So I got this bag with all these crayons in it. Crayon selected, replaced, put back in the bag. Then another selected, find each probability. Okay. Probability of purple would be 14 out of, how many crayons total do we have? Okay, 32 total. So odds of getting a purple is 14 out of 32. But then I put the purple one back in the bag, pick out a yellow one. 6 out of 32. That is going to be a sizable number. 32, I think that's 1,024. I better double check. Oh, we're sharp this morning. Okay. And then I go ahead and reduce that down as far as I can. So it's a little bit easier to look at when you have 2 separate things going on. However, when you get 2 of the same, sometimes you can get tempted to do something silly. Like here, 2 purples, 14 out of 32. The second one will be the exact same thing because I put the purple one back in. So once I do that and I simplify it, I'll go a little ahead on this one just so we can get down to business here. But once I multiply, my numbers would be bigger at the start, but then when I reduce them, that's going to be my reduced answer. But again, that's if I replace them. However, if I do the same exact things from above here, so same numbers of crayons, everything else, however, it's not replaced. It means I don't put it back in the bag. So, for instance, I take a yellow crayon, so 6 out of 32. Then I take a red. Now, there's still, all the red crayons are still available, so there's still 8. But now there's only 31 crayons left in the bag because the yellow one I pulled on the first one's out. It's not in there anymore. That, I don't think I can do in my head. I probably... And then reduce that down as far as you can. But again, I have to pay attention because that one word not changes everything. Because, for instance, and we'll do... Ooh, I see what I want to do for sure. Okay, we're going to do 19 and 21. So, probability of 2 reds. Okay, I got to pull back down here for a minute. There's 8 red crayons, so 8 out of 32. Would it? It would, because this time I've pulled a red out of the bag. So now there's only 7 left. So if I want to try and get another one of that same color, I have to take that into consideration. And I get to my answer that way.
You said 19 equals 21?
Yep, we're going to do number 21, and then I'm going to give you a chance here to kind of play with these a little bit. So last one, we're going to get bust into the cards here again. Cards drawn from a standard deck not replaced and another's drawn. What's the probability of choosing a heart? Still 13 out of 52. Then a spade. Okay, there's 13 of them, but now there's only 51 cards in the deck. And again, I'm just going to give you the reduced form here, since you'd have to reduce anyway to be able to get to my solution. So as you can see, for the most part, today is just basically going to be a review day. But on that worksheet, there are a couple, like that one we did on the front, where you may have to write some of the information out to figure things out. It may not just be straight, here it is, here's my answer, here's how it works, and kind of go that way. So work through that, continue to go. Again, there is going to be another quiz that has this stuff, so having the homework just gives you a little more flexibility with the grade.